Hello everyone, my name is Antonio Coleman and I would like to welcome you back to my channel once again. However, in case you are watching one of my videos for the first time, I use this channel as a way to explore and also explain various computer science topics and concepts in hopes of creating simple yet informative videos. In this video specifically, I will be covering input and output devices as well as the system bus. Now let's begin. Input devices can best be understood as senses for computers. Much like how we use our eyes and ears to take in information around us, a computer uses input devices to receive data and also instructions from users. Some examples of input devices can include things like your mouse or keyboard, also your microphone. They are important because they allow us to interact with the digital world. Most importantly, without them, a computer would be a closed box, capable of processing data, but unable to receive any direction or new information from users. Now we can move on to output devices. These will be better understood as the computer system's voice and expressions. Some examples of output devices that you should be familiar with include things like printers, speakers, and also headphones and monitors. Now that we've familiarized ourselves with these devices, it is important to remember that without output devices, a computer could perform millions of calculations per second. However, you would have no way of seeing the results. The reasoning behind this is because they are necessary to translate the computer's internal thoughts or binary code into a format that humans can perceive through sight, sound, or touch. We can now move on to discuss the role of device controllers and their significance in managing both input and output operations. Device controllers serve as the essential bridge between the CPU, also known as the central processing unit, while also being able to manage specific hardware components as well. These specialized electronic units are responsible for managing the intricate details of both input and output, or I/O, operations by effectively shielding the main processor from the low-level complexities of different hardware protocols. Now, let's move on to our next topic, the system bus. The system bus acts as the primary communication highway of the computer. It is a set of parallel wires or electronic pathways that connect the CPU, memory, and various input and output controllers. It's important to note that without this backbone, the individual components of a computer would exist only in isolation. As a result, this would leave them unable to exchange the data necessary to execute even the simplest commands. To manage this traffic efficiently, the system bus is typically divided into three specialized pathways: the data bus, which carries the actual information being processed; the address bus, which specifies where the data needs to go and also identifies specific memory locations or devices; and the control bus, which transmits signals that coordinate the timing and type of operation, such as read or write. Finally, let's move on to the last topic of this video: synchronous versus asynchronous bus architecture. A synchronous bus includes a specific line for clock signal and allows for all data transfers to occur at a fixed interval, which is determined by the clock pulses. If you're wondering how this works, essentially a read or write operation has to start and finish within a specific number of clock cycles. Some advantages here include simplicity. This is because everything happens on a beat, which means that the logic required to implement it is relatively straightforward. In addition, high speed is another advantage because when connecting components that operate at similar speeds, like a CPU and its local cache, synchronous buses are incredibly fast because there is no negotiation time. However, some disadvantages include clock skew. This happens on very long buses where the clock signal might reach different components at slightly different times. This results in the causing of errors. Another disadvantage is the slowest member, which is a problem where the bus speed is limited by the slowest device on the chain. For example, if a fast CPU is talking to a slow legacy drive, the entire bus must wait for that device to keep up with the clock. Now, as we look at asynchronous bus architecture, we notice that it works by the sender sending a ready signal and the receiver sending back an acknowledged signal once it has captured the data. One advantage that asynchronous bus architecture holds is flexibility. This is because it can easily connect a wide variety of devices operating at vastly different speeds, which a synchronous bus structure does not allow for. We must also account for scalability. This is an advantage because it isn't as susceptible to the physical limitations of clock skew, making it better for longer physical distances and also more complex expansion setups. Notably, some disadvantages include complexity overall. By this, I'm referring to examples such as the handshaking logic, which covers request and acknowledge, which we talked about earlier, requiring more sophisticated circuits in every controller. The next disadvantage that I'll cover is overhead. This is because every single transfer requires extra steps for the handshake. As a result of this, we can see slower speeds than synchronous bus, which is better for high-speed, localized communication. However, this concludes my video. I would like to say thank you for watching. Please feel free to like, share, and subscribe, and come back to my channel for more videos like this. Thank you.